Okay, so so we can start now. So now I would like to welcome our next speaker and also the last speaker for today, Professor Vasilius Dracopoulos. I'm sorry for the pronunciation if it is not coming as it should be. So the Professor Vasilius is uh, working at Department of Computer Science and Biomedical Informatics, University of Thessaly, Greece. The title of his talk is A Fixed Point Theorem for Rho F star Contraction in Complete B Metric Spaces. So I would like to welcome the professor. So over to you, Professor.
Hello, everyone. Thank you very much. First of all, I would like to thank the organizers for giving me the opportunity to present our work, our joint work with Songchol Kwon, Jin-Song Kim, and Song Lee. This is an outline for our talk. First of all, an introduction, then some preliminaries, mathematical work, historical background, and finally, our main results. Let's give a synopsis of this talk. We try to investigate the existence and uniqueness points for these rho hyphen F star contractions in complete B metric spaces. We introduced the notion of rho hyphen F capital F star contraction in a complete B metric space and prove, this is our main result, that every such mapping admits a unique fixed point. If we had the time, but we don't have any, we would show that the Hutchison-Barsley operator associated with an iterated function system built from these contractions possesses a unique attractor, a test that is a unique fixed point. So let's try to define the capital F contractions. This is a work from Wardowski. Let capital F bold be the family of all F capitals from the positive real numbers to the real numbers, such that F1, this is the first property, capital F is stringly increasing, that is for all R, comma T, that belong to the positive real numbers, such that from R less than T, we have F capital R less than F capital T. The second one, the second property, for each sequence alpha n of positive numbers, limit of alpha n is equal to 0 if and only if the limit of F capital on alpha n sequence is equal to minus infinity. And the third one is that there exists alphas that belong to the open interval 0, 1, such that the limit of tau to the alpha multiplied by F capital T is equal to 0 when T tends to 0 from the right, to 0 plus. So let XD be a metric space, a mapping W from X to X, to capital X, is said to be an F capital contraction on XD if there exists F capital that belongs to the bold F capital and tau greater than 0, such that for all x, comma y that belong to x, the distance from wx and wy is greater, when the distance is greater than 0, then taf plus f capital on the d wx, comma wy is less than or equal to f capital of d xy. This is equation 1. This is the definition of F capital contractions. From property F1 and equation 1, it is easy to conclude that every F capital contraction T capital is a contractive mapping, that is, the distance of the images T of x, T of y is less than D of y, xy, for all xy's that belong to x capital, when tx is not equal to ty. So Twardowski stated a modified version of the Banach contraction principle. Let x capital D be a complete metric space, and let W, a self-mapping, be an F contraction. Then W has a unique fixed point x star, and for every x that belongs to x capital, the distance of the W to the nth iterates of W on x, comma x star is equal to 0 when n tends to infinity. In 2014, Twardowski and Van Dang introduced the notion of an F capital weak contraction and studied the existence and uniqueness of fixed points of F capital weak contraction that generalize the aforementioned contractive condition for F capital. The same year, Piri and Kumam proposed another condition instead of the F capital contractive condition of Twardowski to construct a new reduction condition. This is F3 prime. F capital is continuous in semi-closed 0 plus infinity. They denoted by F, bold F, capital star, the set of F capital star functions from the positive real numbers to the real numbers, satisfying conditions F1, F2, and F3 prime, and define the following generalized contraction by considering a new version of theorem 2.1. First of all, definition, let F star capital that belongs to F star capital bold. The mapping W, the self-mapping W, is called F capital star contraction. If there exists stuff greater than 0, such that for all xy that belong to x capital, the metric space, if the distance wx from wy is greater than 0, this implies that taf plus f capital star d, the distance from wx and wy, is less than f star and the distance of on the distance of xy. And then they prove the following theorem. Let xd be a complete metric space and let w self-mapping be an F capital star contraction. So then W has a unique fixed point x star, and for every x that belongs to x capital, the metric space, the distance from the nth iterate of W to the x star is equal to 0 as n tends to infinity. Now the rho hyphen F capital star contractions. In 2024, Shakar et al. Introduced the concept of rho hyphen F capital star contraction, which was a new generalization There exist a lot of generalizations of F and F star contractions. Let's just define the notion. The mapping S capital self-mapping is called rho hyphen F capital star contraction for rho, a self-mapping from R to R. If we have for all xy that belongs to x, if the distance from Sx to Sy greater than 0 implies that F capital star on a distance of Sx Sy is less than or equal to rho F star dxy, where F star, F capital star, belongs to F capital star bold, and the mapping rho satisfies the following three conditions. Rho is an increasing function over the entire domain. Rho is continuous, and for all t that belong to R, rho of t is less than t. We denote by delta, by capital delta, the set of all rho satisfying the conditions A, B, and C. Considering rho of t equals to t minus tau, definition 3 is a generalization of definition 2. The same authors also proved another fixed point theorem by using the following lemma. For any rho that belongs to delta, to capital delta, and t belongs to r, the real numbers, we have that the limit of the enthalpy rate of r of t is equal to minus infinity as n tends to infinity. And now the theorem, let x comma delta, d be a complete metric space and capital S, the self-mapping from here to itself, be a rho hyphen F capital star contraction by rho that belongs to delta and phi belongs to F capital star, then S capital has a unique fixed point x star for x, the limit of the enthalpy rate of S on x is x star as n tends to infinity. And now the B-metric spaces. All this is the historical background of the work. A B-metric space is a generalization of a metric space where the standard triangle inequality, the distance from x to z is less than the distance from x to y plus the distance from y to z, is relaxed to the distance from x to z less than a coefficient s by dxy plus dyz for a constant s that is greater than or equal to 1. Introduced by Bakhtin, 1989, and Czervik in 1993, this space allows for larger distances with s equals to 1, reducing it to a standard metric space. More formally, let X be a non-empty set, capital X, a mapping D from X times X to the zero closed in the semi-closed interval plus infinity is called a B-metric if for all x, y, z's that belong to x, the following conditions. The first one is that when we have the distance from x to y is equal to 0, this means that x is equal to y and vice versa. dxy is the distance from x to y is the same as the distance from y to x, and the triangle distance, the relaxed triangle distance that I told you before. Then xd is called a B-metric space. Some more things to define. Let xd be a B-metric space and let the sequence of points in xd be xn x belongs to x, then if the limit of dxn x is equal to 0, the sequence is said to be convergent to the point x. If the limit of dxn xm is equal to 0, xn is called a B-Cauchy sequence. If any B-Cauchy sequence of xd is B-convergent in xd, then xd is called a complete B-metric space. And the theorem, let xd be a B-metric space with coefficient s greater than or equal to 1. It has the following properties. Xn has a unique limit if it is B-convergent to the point x, and a B-convergent sequence is a B-Cauchy sequence. A B-metric is not continuous in general. And now this is part of our work. This is part of the main results of our work. Let us define rho hyphen capital F star contractions in B-metric spaces this time, not in general metric spaces. Let XD be a complete B-metric space, and for the mapping S is called a rho hyphen F capital star contraction if we have for all xy that belong to x capital, the distance s x from sy greater than 0 implies that F capital on D Sx Sy is less than or equal to rho on F on epsilon, a small epsilon, epsilon positive, by dxy, where F capital belongs to F capital star and rho belongs to delta, to capital delta. Our main theorem is theorem 4.1. Let xd be a complete B-metric space, and let the mapping S capital from x to x be a rho hyphen F capital star contraction with epsilon is less than or equal to 1 over S. S is the coefficient, not the capital S. Then S has the capital S has a unique fixed point x star, and for every x that belongs to x capital, the limit of the nth iterate of S is equal to x star as n tends to infinity. This is the proof. I have the proof also. I think it is not time. We don't have enough time to analyze the proof and tell you this. Believe me, it's correct. But I can tell you an example. I can give you an example. Let A be a set, the set 0, 1, square root of 1 over 2, square root of 1 over 3, and so on, 1 over square root of 1 over n. And we define the distance d on the set A as dxy be the maximum of x squared, y squared. Then A, D, is the pair AD is a complete B-metric space with S equals to 2. Also, we can define the mapping S from A to A as follows. S on square root of 1 over n is equals to the square root of 1 over 2 by 1 plus n. This satisfies the rho hyphen F capital star contractive conditions with respect to these three. First of all, F capital T is the logarithm of T when T is greater than 0. Rho of T is the logarithm of E to T over ET plus 1, and epsilon is equal to 1 over 2. And so it has 0 as a unique fixed point. I have also here the proof of this result. And let's say some remarks. In example 1, the mapping S capital is not a Banach contraction. Since D of S of square root of 1 over n and square over 1 over m is equals to 1 over 2 by 1 plus n. ED is equal to ED of these two, the square root of 1 over n and square root of 1 over m is 1 over 2n plus 1, holds for every n m that belong to A, and this limit is equal to 1. So it is not a Banach contraction. Another remark is that in example 1, the mapping S is not a capital F star contraction. Since F capital is continuous on 0 plus infinity, open, there is a delta greater than 0 for any theta greater than 0. X belongs to 0 plus infinity, so that the absolute value of fx minus fy is less than theta, holds for any y that belongs to 0 plus infinity, with the absolute value of x minus y is less than delta. Taking the square root of 1 over n and the square root of 1 over m less than delta, we therefore have that taf is less than this one. This one is f capital 1 over 2m minus f capital 1 over 2 by m plus 1. And since 0 is less than 1 over 2 m minus 1 over 2 by m plus 1 less than delta, we get that taf is less than theta. Thus, we can take t taf greater than 0, so it is not a capital F star contraction. And we have some corollaries, some interesting corollaries. Let XD be a complete bimetric space and suppose there exists taf greater than 0, such that for the mapping S capital for all xy belongs to x, the distance Sx to Sy, this is capital S, so capital S here, y that greater than 0, we have that this implies that taf plus capital F star, the distance on the distance Sy, Sx, Sy is less than F capital E times d xy. Then the mapping S has a unique fixed point at x star, and this limit is x star for all x that belongs to x capital. F capital star belongs to F bold capital star. Rho belongs to delta capital delta, and epsilon is less than 1 over S. This follows directly from theorem 2.2 with rho equals to T minus taf. And the second corollary, let XT be a complete metric space. Suppose for the mapping S, we have almost the same, that for all xy, we have the distance from Sx, this is capital S, Sy, greater than 0. This implies that F on D, Sy, Sx is less than rho on F on D, xy. Then the mapping S has a unique fixed point x star, and this limit is x star for all rho and F capital star. And the proof is very easy. Since S is equals to 1, it can be easily proved from theorem 4.1 by taking epsilon equals to 1. Thank you very much for attention. If we had time, I have a lot of applications on fractals, but I think
Yes,
it's our
uh, yes, Professor, you can take some more time because the next talk is already cancelled. So you can take some more time if you want.
yes. Just I don't have it on the. I don't have them the applications on slides, but I can give you a, a glance, a speaking glance
Yeah,
of,
okay.
of the yes. I can give you radiophonic transmission. So the applications on fractal spaces is that we show that the Hutchinson-Basley operator consisting of a finite, as you know, finite number of contractions, but finite number of rho hyphen F capital star contractions in a complete bimetric space has an attractor, has a limit set. So we have proven a theorem which shows the existence and uniqueness of the attractors of iterated function systems. And the theorem is mainly as follows. We have the complete bimetric space. We have the WI as usual, but this WI is not continuous or contractions, Banach-like contractions. Now they are rho hyphen F capital star contractions. And we have the usual iterated function system. Then the Hutchinson-Basley operator, we prove that the Hutchinson-Basley operator H capital, W capital, has a unique fixed point, and for every set that belongs to the Hutchinson, that belongs to the set of the fractals, the H calligraphic of X, the family of all compact sets of bimetric spaces. This Hutchinson-Basley operator, capital W, the antiterate of capital W of A, converges to the attractor of this set of the H calligraphic of X. This is the main part of the applications. We have some corollaries, examples, and so on. Thank you very much for your attention, and I hope that everything will be fine with your seminar, symposium. Thank you very much.
Thank you so much, Professor. So now I would like to request to the audience if they have any quick questions. So if not, so let's thank the speaker. Thank you, Professor, for the talk.
Thank you.